Previous class we have discussed about the effect of current on current and we define 1 ampere. Now today we are going to discuss the torque on a rectangular current. Torque on a rectangular current loop in a uniform magnetic field. We are going to show that if we place a rectangular current carrying loop in a uniform magnetic field, then the net force acting on the loop will be 0, but there will be a torque acting on the loop, and now we are going to deduce that expression for the torque. Now let us see. Let us draw the picture. Let us say here is a region in which there is a magnetic field, uniform magnetic field of strength B. Clear? And here is a rectangular current carrying loop. Let us say PQRS. PQRS is a rectangular current carrying loop in which I current is flowing in anti-clockwise direction. This anti-clockwise direction, right? Let us say length of the loop is L and breadth of the loop is B. B is the breadth and L is the length of the loop. Again, let us say in a particular moment the normal to the plane of the loop makes an angle theta with the direction of the magnetic field. That means if this is the PS arm, then this PS arm, rather we can, you have to think this as 3 dimension. Let us show you something, otherwise you cannot, you may not understand this. Let us say this is an current carrying loop, right? And here let us say from in this direction, or if I going to compare with my figure, then let us say in this direction there is a magnetic field. If the loop is placed in this position, then the direction of magnetic field is perpendicular to the normal to the plane of the loop, right? This is the normal to the plane of the loop and this is the direction of magnetic field, and this makes an angle 90 degree. Now if this makes an angle like this, then what happens? Then this is B, right? And this is the direction of the normal to the loop, right? Or if you say in this position, then also see here, this is the, okay, this side is much better to you. This is the direction perpendicular to the loop, right? This is what? This is theta. This is the normal to the plane of the loop, and this was the what? Direction of B. Clear? Now if this angle is theta, what angle? B and the normal to the plane, then this also theta. That means you can say this angle is theta. Okay? This angle is theta and this is B, right? Therefore this arm is B sin theta. Okay? What we have till now told that we consider a rectangular current carrying loop carrying current I placed in a uniform magnetic field of strength B, whose length is L and breadth is B. Now we are going to show that this loop does not experience a net force, but it will experience a torque, right? And this is analogous to that of our electric dipole placed in an uniform electric field. If we place an electric dipole in a uniform electric field, then net force acting on the dipole is zero, but it will experience a torque like that. Clear? Just recall that result. Electric dipole in any uniform electric field. We have already discussed that electric dipole experiences no force, but it will experience a torque, and that torque will try to align the dipole in the direction of electric field like that. Let us consider a rectangular loop PQRS of length L and breadth B placed in an uniform magnetic field of strength B, and theta is the angle between the normal to the plane of the loop and the magnetic field B. Right? Now we have already deduced an expression for the force on a conductor of length L carrying current I in a magnetic field B. What was that? A straight conductor of length L carrying current A, if placed in an uniform electric field B, then it will experience a force. And what was that force? We have deduced that. F was, we have written that as IL cross B. Right? That was the expression. And from here you get ILB sin theta. Right? If the length is L, then IL cross B. Now, the force on QRR. Now we are going to calculate the force in different arms of this rectangular loop. The force on QRR, let us say F3 in this arm. What will be the force? Force will be I into B cross B. I into B cross B. This is the force. And see here, this is the direction of B, and this is what? Capital B. B is magnetic field, and this is the direction of small b. Now B cross B, from the lower side you rotate anti-clockwise, then the force will be acting downward, right? That means force on this arm will be along this direction. Clear? Is it? Again, force on PSR. Let us say that force is F4. This is also I into B cross B. And again you apply the right hand screw rule, and you will get the force is on the upward direction. Now see here, we have this is the rectangular loop, right? This was my rectangular loop, and force on this arm is acting upward, force on this arm acting downward, and both the forces are on the same line, and also has the same magnitude. The two forces have the same magnitude, F3 and F4, and they are in the opposite direction and also acting on the same line. So they cancels each other. They cancel each other, right? That means F3 and F4 force, that is the force on the arm QR and force on the arm SP, are equal and opposite and acting on the same line. Therefore, this leads to the zero force and also zero torque, since the line of force same. Line of forces are same, so torque is also 0. Now, forces acting on PQ1 and RS1. The force on the PQ1, let us say F1. F1 is the force on PQ1, and that will be IL cross B, right? IL cross B. And what will be the direction? See here. This is the IL and this is B. Therefore, it will in which direction? See here, both are perpendicular. IL cross B. You rotate it anti-clockwise, right? And it will come out of the board. Therefore, this force, magnitude of this force is F1 is equal to ILB, and it is perpendicularly out of the board. Force on RSR. Force on RSR is F2 is equal to again IL cross B, and magnitude of that force is ILB, but what will be the direction? See here, this is B, right, and this is ideal. Now ideal cross B, you rotate clockwise, then the screw advances into the board. Therefore, direction of this force is into the board. This is the direction of the force. Now again, F1 and F2 are also same. Magnitude is same. Direction is opposite. So net force is 0. Therefore, net force on this rectangular lobe is 0. F3, F4 produces 0 force and F1, F2 produces 0 force. Therefore, the total force on the forearms, that is the total force acting on the rectangular lobe, is 0. But in this case, the line of force are different. F1 and F2 acts in different line. So they form a couple and try to rotate the loop. In anti-clockwise. See here. Try to rotate the loop anti-clockwise. Right? And net force acting on the loop is 0. The magnitude of the torque acting on the loop is what? Magnitude. What will be the magnitude? Magnitude will be force into perpendicular distance. Now force is, one of its force is ILV, and this is the perpendicular distance, B sin theta. This is the perpendicular distance between the forces F1 and F2. So we get I into LB into capital B into sin theta, and LB is the length into breadth of the rectangular loop, that is area of the loop, or we can say tau is equal to IAB sin theta. This is the magnitude of the loop. And what is the direction? Direction is it will rotate anti-clockwise, and from that you can write tau is equal to, this as IA cross B. A is the area vector. We know what is the area vector, and B is the uniform magnetic field strength. Now this is the vector form of the torque acting on the loop. Now if the loop has n turns, then net torque acting on this loop will be equal to, if n turns, then it will be NIA cross B, or you may say magnitude of this is NBIA sin theta. This is the net torque acting on a rectangular loop of n turns placed in an uniform magnetic field is tau is equal to NBIA sin theta. Okay, now we have deduced the expression for the torque on a rectangular current loop in a uniform magnetic field. If the loop has other shape, that is, it is not a rectangular loop. It may have another shape, may have circular, may have elliptical, or any other shape. In all cases, we can prove that the torque on a current carrying loop is equal to this, tau Ia cross B. B is the magnetic field strength. Now recall your expression. Recall your expression for the torque acting on an electric dipole placed in an uniform electric field. What was that expression? That was tau was P e sin theta, that is P cross E. And what was P? Dipole moment, right? That was dipole moment, rather electric dipole moment P was, right? Now compare these two. Compare these two expressions. Tau E is P cross E and tau is Ia cross B. If we replace this term Ia by capital M, which is dipole moment of this loop, if we replace that by M, then this expression is analogous to this expression, where M, capital M, is I into A, can be defined as the magnetic moment of this current carrying loop. And from here, we can say that a current carrying loop may be considered as magnetic dipole.